Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual ferment of the 1930s, a decade that witnessed the very foundations of physical reality being redrawn, the atomic nucleus presented a profound and unsettling paradox. Following James Chadwick's 1932 discovery of the neutron, the picture of the nucleus as a dense congregation of protons and neutrons became standard, yet this model contained a glaring contradiction. The colossal electrostatic repulsion between the closely packed protons should have torn the nucleus apart with unimaginable violence. The known forces of nature, the feebleness of gravity and the repulsive character of electromagnetism, offered no cohesive explanation. A new force was required, one of a truly gargantuan strength, yet one whose influence vanished almost completely beyond the nuclear boundary. This was the landscape of theoretical desperation into which a young, solitary physicist at Osaka Imperial University, Hideki Yukawa, introduced a conceptual leap of breathtaking audacity. His 1935 paper, titled On the Interaction of Elementary Particles, I published in the relatively obscure Proceedings of the Physico-Mathematical Society of Japan, did more than solve the puzzle of nuclear stability. It proposed the existence of a new class of matter and established a universal principle for the nature of forces, a principle that would become the very grammar of modern particle physics. Yukawa's work stands as a testament to the power of physical analogy and mathematical intuition, a singular act of theoretical creation that predicted a particle from the properties of a force, forever altering our conception of the subatomic world. The genesis of Yukawa's theory lies in the fertile ground prepared by the twin revolutions of relativity and quantum mechanics, and more immediately, in the theoretical frameworks developed to describe the atom's other constituents. The most potent conceptual precedent was quantum electrodynamics, or CAD, which described the electromagnetic interaction as a continuous exchange of virtual photons between charged particles. The photon, a massless quantum of the electromagnetic field, served as the messenger or carrier of the force. This elegant and powerful idea, however, seemed confined to its own domain. The nuclear force was a different beast entirely. Its defining characteristic, its incredibly short range of approximately 1 to 2 femtometers, stood in stark contrast to the infinite reach of electromagnetism. Physicists like Werner Heisenberg had posited that the force binding protons and neutrons arose from some form of exchange mechanism, treating the two nucleons as different quantum states of a single entity, but the identity of the exchanged particle remained a complete mystery. A second crucial piece of the intellectual puzzle was provided by Enrico Fermi's 1934 theory of beta decay. Fermi's theory described the transformation of a neutron into a proton through the emission of an electron and a neutrino. Its most radical implication was that particles could be created and annihilated. The electron and neutrino were born in the moment of decay. They were a manifestation of the underlying quantum field, a departure from the classical prejudice that all particles are permanent, immutable objects. This concept of particle creation liberated Yukawa's thinking, allowing him to postulate a new particle whose existence was transient and whose purpose was solely to mediate an interaction. He saw that if the electromagnetic field had its quantum, the photon, then the new nuclear field must also have its corresponding quantum. Yukawa's 1935 paper is a model of deductive elegance, proceeding from a single profound insight. He began by explicitly taking the electromagnetic field as his template and asking what mathematical modification would be necessary to transform its infinite-range potential into a short-range one. The standard electrostatic potential, the Coulomb potential, is a solution to the Laplace equation. Its form, which is proportional to the inverse of the distance, 1 over r, ensures its gradual weakening but limitless extent. Yukawa reasoned that this mathematical structure was a direct consequence of the mediating photon being massless. For his new nuclear field, he chose a different starting point, the Klein-Gordon equation, a relativistic wave equation suitable for describing particles with mass. He sought a static, spherically symmetric solution to this equation, mirroring the form of the Coulomb potential. The result of this calculation was the celebrated equation that now bears his name, the Yukawa potential. In its mathematical form, V of r equals a constant, g squared, multiplied by the quantity e to the power of negative kappa r, all divided by r. Here, g represents the strength of the interaction, the coupling constant, and r is the distance between the nucleons. The crucial new element was the exponential decay term, e to the power of negative kappa r. This term acts as a powerful damping factor, causing the potential to fall off with extreme rapidity as distance increases. The constant kappa in the exponent determines the precise range of the force. A large kappa corresponds to a very short range, while a kappa of 0 would recover the infinite range Coulomb potential. This was a masterful piece of theoretical engineering, But Yukawa's genius lay in taking the next step. He inverted the logic. Instead of merely describing the force, he used the known properties of the force to predict the properties of its unknown carrier particle. The constant kappa in his potential was related to the mass of the hypothetical exchange particle. By a simple and beautiful formula derived from fundamental quantum principles, the mass, m, is approximately equal to the reduced Planck constant, h stroke, divided by the product of the range of the force and the speed of light, c. One can also express this as the mass m equals the reduced Planck constant times kappa, divided by the speed of light, using the experimentally estimated range of the strong nuclear force, about 1.4 times 10 to the power of -50 meters. Yukawa performed the calculation. The result was astonishing. The mass of his proposed particle, which he initially called the U-quantum, was roughly 200 times the mass of the electron, yet still about 9 times lighter than a proton. It was a particle of an entirely new weight class, intermediate between the known light particles, the leptons, and the heavy particles, the baryons. He had predicted the existence of what would come to be called the meson, derived from the Greek word for middle. Furthermore, his theory predicted that this particle could be charged, mediating a force between a proton and a neutron, or neutral, mediating a force between two like nucleons. The initial reception of Yukawa's paper was one of profound silence. Published in a Japanese journal with limited Western circulation, and proposing a particle that no one had ever seen, the theory was deemed by many to be an exercise in pure speculation. The world of physics was still grappling with the positron and the neutron. The appetite for new additions to the elementary particle zoo was low. A story, perhaps apocryphal but illustrative, tells of Niels Bohr's visit to Japan, where upon hearing of the theory, he expressed deep skepticism. The theory's solitude, however, was dramatically broken in 1937. Working with cosmic ray data, Carl Anderson and Seth Nedmeyer at Caltech, and independently J.C. Street and E.C. Stevenson at Harvard, discovered a new particle. Its mass, measured to be about 207 times that of the electron, was in uncanny agreement with Yukawa's prediction. It seemed a stunning and rapid vindication of his theoretical vision. The particle was christened the mesotron, and for a time it appeared that the nuclear force problem was solved. Yet nature, in a move of almost theatrical misdirection, had presented physicists with a frustrating puzzle. As more was learned about this cosmic ray particle, it became clear that it was an imposter. The carrier of the strong nuclear force should, by its very nature, interact strongly with atomic nuclei. The newly discovered mesotron, however, showed a perplexing indifference to nuclear matter, penetrating thick layers of lead with ease. It interacted weakly, more like a heavy electron than a robust glue of the nucleus. This discrepancy plunged the field into a decade of confusion, a period where the theory seemed both brilliantly confirmed by the particle's mass and fatally contradicted by its behavior. The resolution to this paradox was as elegant as the initial theory, and it solidified the predictive power of Yukawa's framework. During and after the Second World War, a group of Japanese theorists, including Shoichi Sakata and Yasutaka Tanikawa, and independently in the United States, Robert Marshak and Hans Bethe, formulated the two-meson hypothesis. They proposed that Yukawa's strongly interacting meson was indeed being created in high-energy cosmic ray collisions in the upper atmosphere. However, this primary meson was highly unstable, decaying with incredible speed into the lighter, weakly interacting secondary meson that was being detected at sea level. The particle discovered by Anderson and Nedmeyer was the decay product, a granddaughter of the true nuclear messenger. The hunt was now on for the parent particle. The breakthrough came in 1947. A team led by Cecil Powell at the University of Bristol, using a new and powerful technique involving stacks of photographic emulsions flown to high altitudes on mountains, captured the entire event on film. Their plates showed tracks of a heavier meson, which they named the pion or pion, coming to rest and then decaying into a second, lighter meson. The pion interacted strongly with nuclei, just as Yukawa's particle should. The second particle was the familiar weakly interacting particle from cosmic rays, which was subsequently renamed the muon. At last, Yukawa's prediction was fully vindicated. His theory was now a cornerstone of nuclear physics, and he was awarded the Nobel Prize in Physics in 1949 for his prescient. The enduring legacy of Yukawa's 1935 paper extends far beyond the discovery of the pion. Its central thesis, that every fundamental force arises from the exchange of a quantum field particle, became the organizing principle for all of particle physics. It was a profound conceptual shift. Before Yukawa, forces were fields and particles were matter. He blurred the line, showing that the agents of force were themselves particles. This paradigm now underpins the standard model of particle physics. The electromagnetic force is mediated by the photon. The weak nuclear force responsible for radioactive decay is mediated by the massive W and Z bosons, and the strong nuclear force is ultimately mediated by gluons. The W and Z bosons, discovered in the 1980s, were in a sense heavy cousins of Yukawa's meson, their large mass explaining the extremely short range of the weak force. The modern theory of the strong force, quantum cryptodynamics or QCD, is vastly more complex than Yukawa's simple model. In QCD, protons and neutrons are composite particles made of quarks, and the fundamental force is carried by gluons acting between these quarks. The pion of Yukawa's theory is now understood as a residual, effective manifestation of this deeper interaction, much like the van der Waals forces between neutral atoms are a residue of the fundamental electromagnetic forces within them. Nonetheless, Yukawa's theory remains a brilliant and quantitatively successful effective theory for nuclear interactions at low energies. It was the first crucial step on the path to understanding the subatomic universe, a foundational idea that provided both the language and the direction for decades of subsequent research. While the details have been refined and the cast of characters expanded, the essential plot of interaction via particle exchange remains the one he first authored. In conclusion, Hideki Yukawa's On the Interaction of Elementary Particles represents one of the great intuitive triumphs in the history of science. Emerging from a state of theoretical crisis concerning the stability of the nucleus, his work provided a solution that was at once simple, radical, and profoundly generative. By creatively adapting the mathematics of the electromagnetic field, he postulated a massive force-carrying particle and, from the known dimensions of the nucleus, calculated its mass with remarkable accuracy. This act of pure theory not only predicted the existence of the meson but established the exchange particle mechanism as the fundamental paradigm for understanding forces. The journey from his proposal in 1925 through the confusing interlude of the muon to the final discovery of the pion in 1947 is a classic saga of scientific prediction and confirmation. Yukawa's insight transformed the landscape of physics, opening the door to the rich and complex world of subatomic particles that lay hidden within the nucleus. His theory serves as the conceptual ancestor to the entire Standard Model, and his method of inferring particles from the characteristics of their fields continues to inspire theoretical physicists today. It was more than an explanation, it was a new way of seeing, a framework that taught physics how to think about the fundamental machinery of the universe.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.